Hello everyone. Before diving into today's topic, we want to take a moment to thank you for your support. Every like, comment, and subscription really makes a difference and helps this channel grow. If you enjoy our content and don't want to miss future videos, subscribe to the channel and activate the bell to receive all notifications. Imagine a clear night, far from the city lights. You look up at the sky, and for a moment, you feel part of something immensely greater. Millions of stars dot the infinite darkness, each one distant, unreachable. For millennia, humans have gazed at those flickering lights with a mix of wonder and melancholy. Too far to reach, too mysterious to fully understand. And yet today, for the first time in history, we are no longer condemned to merely contemplate the universe from afar. A bold idea is taking shape in the world's most advanced laboratories. A technology that could break the boundaries of interstellar space. Its name is Sunbeam, and it promises to take us where no probe has ever dared to venture. Not in centuries, not in an undefined future, but within a few decades. The goal? To reach star systems like Alpha Centauri in just 40 years. A time span compatible with a human life. A time we could live through, witness, and recount. To understand the scale of this endeavor, we must first confront a simple truth: space is big. Immensely big. 1 light year equals 9.46 trillion kilometers. Even our fastest probes, like Voyager 1, launched in 1977 and currently the farthest man-made object from Earth, haven't traveled a single light year yet. After nearly 50 years of journeying, the distance separating us from the stars remains an apparently unbridgeable abyss. But what would happen if we could travel at 10% the speed of light? And if a space probe could move at 30,000 kilometers per second, over 100 million kilometers per hour? In that case, Alpha Centauri, 4.37 light-years away, would no longer be a remote dream but a reachable destination within a single generation. This is the promise of Sunbeam. Sunbeam's logic is radically different from traditional systems. Current probes carry all the fuel needed for their journey. This implies huge limits. The more fuel needed, the more weight is added, reducing efficiency and speed. Sunbeam, instead, eliminates onboard fuel. Energy is provided externally, in real time, by an orbiting platform called a solar statite. This extraordinary device stays suspended near the Sun thanks to solar radiation pressure and magnetic fields, functioning like a cosmic pump that sends a constant flow of relativistic electrons to the probe. These electrons, accelerated to near light speeds, transfer continuous thrust to the probe, gradually bringing it to a velocity no human-made vehicle has ever reached. A silent, invisible impulse capable of breaking the barriers of distance. One of the main issues with such a system is evident. Electrons, by their nature, tend to repel each other due to their negative charge. How can a beam of particles be kept compact in the vacuum of space over billions of kilometers? The answer comes from Einstein's special relativity. Thanks to the so-called relativistic pinch effect, the electron beam remains focused. When particles move at near light speed, time slows down for them. From an external observer's point of view, it seems like the electrons live more slowly, reducing interactions among them and preventing the beam from dispersing. This allows energy to be transmitted precisely, without significant dispersion, over enormous distances. Unlike other projects, such as Breakthrough Starshot, which involves using microbe probes the size of postage stamps, Sunbeam aims to launch a real scientific probe. A 1,000 kilograms vehicle, equipped with advanced instruments, high-resolution cameras, spectrometers, atmospheric analysis modules, and, most importantly, a transmission system capable of sending data back to Earth even from 4 or 5 light-years away. This means obtaining real images of exoplanets, direct analyses of their atmospheres, geophysical measurements, and perhaps even signs of biological activity. One of the main targets is Proxima b, the closest exoplanet to us. Discovered in 2016, it orbits the red dwarf Proxima Centauri and is located in the so-called habitable zone, the region where temperatures allow the stable presence of liquid water. Although it likely has synchronous rotation, with one side always facing the star and one in constant darkness, It is hypothesized that a temperate twilight zone may exist, where conditions could be suitable for life. But it is not the only candidate. Planet K218b, 124 light-years away, drew global attention with the discovery of dimethyl sulfide, DMS, in its atmosphere, a molecule produced on Earth exclusively by living organisms. A probe sent there could help solve one of humanity's oldest and deepest questions: are we alone? Building Sunbeam is no easy task. Every element of the system requires radical innovation. The electron beam must be aligned with millimetric precision for decades. The solar platform must be built with materials capable of withstanding temperatures over 1000 degrees, as well as the sun's intense radiation. The thermoelectric generators, needed to convert solar heat into electricity, are currently only theoretical concepts. Yet we are not starting from scratch. The Large Hadron Collider at CERN already produces relativistic particle beams. Linear accelerators have extremely advanced guidance systems. Probes like the Parker Solar Probe prove that we can send objects very close to the Sun without destroying them. The potential exists. It just needs to be integrated, refined, tested. The implications of Sunbeam's success are not just technological. They are cultural, philosophical, historical. For the first time, humanity would leave its solar system with a precise purpose, a destination, and a concrete possibility of discovering another inhabited world. History books, literature, science, even human spirituality, would have to reckon with a new cosmic reality. Earth would no longer appear as the center of the universe, but as the starting point. The most optimistic estimates suggest that a Sunbeam prototype could be launched within 20 or 30 years. It's not a short time, but it's not utopian either. It's a goal within our reach. And when it happens, when a human-made probe launches toward another star system, it will be like the first boat crossing an unexplored ocean. That probe will carry with it humanity's millennia-old dream. And with every kilometer traveled, every signal transmitted, every image sent back from deep space, it will remind us that, despite our weaknesses and divisions, we are a species born to explore. Because there is no night long enough to forever darken human curiosity. And there is no distance that, one day, we will not be able to cross.